Okay, so in this last video, we're going to talk about the growth constant, and it's going to be a really quick one with a quite long example. So the average rates of growth are represented by chords on an exponential graph. So let's say we had a graph that looks like an exponential that we use. Turn this one off. If I want to look at an average between, let's say, 0 and 2, what I would do is I would draw a chord between those two, and then use that to work out what my average is. So that's what that means. Okay? And an instantaneous rate, as we know, is just represented by a tangent. So if I want to know what the instantaneous rate of 2 is, so here's my value here, somewhere around there. So there's my value of 2 there. I would draw a tangent. And of course, the tangent should, in this case, be a lot sharper than the chord. So the chord would be a lot flatter, and the tangent's going to be quite stronger. And we know this is going to be the case because if something's growing at an increasing rate, then the average, the previous values, are actually going to bring it down a bit. So what this does is it gives us 4 different types of rates. So 2 instantaneous rates, so 1 ordinary instantaneous rate, and 1 proportional, so basically based on a proportion of the exponential amount. And 2 average rates, so 1 ordinary and 1 proportional as well. So here's an example. The cost C of building an average house is rising according to the exponential growth equation. C is equal to 150,000 E to 0.08 T, where T is time in years since 1st of January 2000. Show that d C dt is proportional to C, and find the constant of proportionality. So basically what we're going to show in this case is that the derivative is some proportion. It's directly proportionate to the function itself. So in other words, it's going to be, or I should say that dc, I think it is for cost, is equal to sum A times C, or some amount, so some proportion amount times C. Okay, so that's what our goal is for this first one. So if we differentiate this C with respect to T, so dc dt is equal to, so let me actually just rewrite this one down. So if C is equal to 150,000 e to the 0.08 t, then dc dt is equal to 0.08 times 150,000 e to the 0.08 t. Because remember, the derivative says that the derivative of this comes out the front. And as you can see, that means that dc dt is equal to 0.08 times our cost function. And again, this gives us another one of these differential equations, because we've got the derivative part and we've got the function bit. Okay, so dc dt is proportional to C with a constant of proportionality of 0.08. That's it. Okay, part B. All right, part B out first. Now, part B says, find the instantaneous rates at which the cost is increasing on the 1st of January 2000, 2001, 2002, 2003, correct to the nearest dollar per year, and show that each rate is about 0.833 times the preceding rate. So basically what this means is we're going to be substituting our values into our derivative, because we're after the rate, the instantaneous rates. So our derivative is approximately, well, it is 0.08 times 150,000, which is about 12,000 e to the 0.08 t. Okay, so on January 2000, dc dt is equal to 1200 e to the 0, which is just equal to 1200. Now 2001, our derivative is going to change a bit. So it's going to be 1200 e to the power of 0.08 times 1, which is, if we put it into this calculator over here, 1200 e to the 0.08 times 1 gives us 12,999 to the nearest dollar. Now the change between those is 12,999 minus the 1200 sorry, not minus, divided by the 1200, and this should approximately give us 1 plus that rate that we wanted to find. So in our initial question, we wanted to show that the growth rate is about 0.833 times bigger. So that amount is equal to this, and if I subtract the original starting amount, we should get, not that, if I should subtract the original starting amount, which is 1, oops, now I'm going to do this again. So 12,999 divided by 1200 minus 1, and that gives us our 0.083, which is what we wanted, I believe. Yeah, so the change is 0.0833. Now, the reason why I subtracted 1 is because we're actually looking for the change. So the change is actually, it changes by $999, and we do that over the original amount, which gives us the same value there. So the way I did it, I just said I subtracted 1 from it. Okay, so that was for 2001. So for 2002, our derivative is going to be 1200 to the power, e to the power of 0.08 times 2, which is equal to, so put it in, and if you put it in, I'm going to just use my notes, 14082 per year. And again, by doing this change, okay, the change is going to be, so 14082 minus the amount before equals that. And we're going to divide that by the original amount, or the amount we started with that for that year. And again, we're going to get the change is 0.0833 again. Now the last one we want to do is 2003. So dc dt. So remember, the reason I'm getting, how I'm getting my t's is t is equal to 1 year, because 1 year has passed between here and here. 1 year has passed between here and here, so t is equal to 2, and then again t is equal to 3 for this one. So that's equal to 1200 e to the 0.083, which is equal to, and if you put it into a calculator, you get approximately 152, and I should be doing approximately because these aren't exactly equal, but 15255. Now again, we're going to do the change. So the change in percentage is 15255 minus the amount they started with for that year, and divide it by the amount that they started with for that year, which should give us 0.0833. As you can see, that 0.0833 is constantly the same. It does change a little bit. The actual decimal does change a little bit, but the amount is pretty much exactly the same. So that's part B. Now part C says find the cost of C when t is equal to 1, 2, and 3, and the average increase in cost over the first year, the second year, and the third year, correct to the nearest dollar, geez, I don't know what happened with me in that sentence, per year, and show that each rate is about 0.0833 times the preceding rate. So this time, we're going to do our instantaneous ones. So let's get some values. So this is part C. So the costs, or the values of C when t is equal to 0, t is equal to 1, t is equal to 2, and t is equal to 3 are, so this is substituting it into the original function, so the cost function. So it's this is the first one, and we're going to make life a bit easier. This is the second one, so it's just 1 times 0.08. This is the third one, and the fourth one is e to the 0.24. So those are the 4 values. So that's t is equal to 1, 2, or 0, 1, 2, and 3. Okay, so what we want to do is we want to try and find the increase in the 2 times. Okay, so to do so, for the first year, let's start with the first year. So the first year, the increase is 150,000 e to the 0.08 minus 150,000, which is approximately equal to, so 150,000 e to the 0.08 minus 150,000 is equal to 12493. Okay. Now the second year, so we're just going to follow the same pattern. So the second year, so the second year is going to be 150,000 e to the 0.16 minus 150,000 e to the 0.08, and that's approximately equal to, if we put it into our calculator, we get 13534. And for the third year, the change in that third year, it's going to be 150,000 e to the 0.24 minus 150,000 e to the 0.16, which is approximately equal to 14661. Okay. Now, again, the change between the two is always this 0.08. So I could actually rewrite this with the factors taken out, okay, each time. So in this case, we've got 150,000 e to the 0.08 minus 1. Okay, this one here, we've got 150,000. Now e to the 0.08 is common to both, so that leaves us with e to the 0.08 minus 1 again. And you can see how that factor is always the same throughout the whole of this. 0.8 minus 1. So again, that 0.08 is always there. So e to the 0.08. So e to the 0.08 is approximately equal to 1.033. So again, it's that same value. So if we subtract that from 1, again, it's the same value that was always shown up here. So that's that last bit of the question to show that the rate is about that times. So that's that one there, just by saying, well, each year it increases by e to the 0.08 amount. So as each year it increases by that amount, and so that amount is equal to 0.0833. Okay, so that leaves us with question D. Now question D says, show that the average increase in cost over the first year, the second year, and the third year expressed as a proportion of the cost at the start of that year is constant. So going through that, reading that once more, show that the average increase in cost over the first year, the second year, and the third year, expressed as a proportion of the cost at the start of that year, is constant. Okay, so we want to be looking at the differences at the start of each year, and we want to be showing that it's essentially the same no matter which year you're doing. So we've got 3 proportional increases over the first year. So the first one is 150,000, lots of e to the 0.08 minus 1 over 150,000. Okay, so the new amount over the old amount, which is equal to, so dividing out through that factor of this and this, we're left with e to the 0.08 minus 1. Okay, so it's year 1. So year 2, it's the same sort of thing, 150,000, e to the 0.08, and then e to the 0.08 minus 1 again. So this is this one here, the second year one. Okay, and that's going to be over the 150,000, so the beginning year, which is e to the 0.08. Okay, so that means that this guy is going to cancel with this guy, and we're left with e to the 0.08 minus 1 again. And same thing's going to be for the third year. So year 3 is equal, and etc., etc. Now, the proportional increases are all equal to, so all the increases are equal to e to 0.08 minus 1. So therefore it is approximately equal to 8.33%. And that's that number that we keep popping up with. So that's the end of exercise, or chapter 16b. So we've only got one more to do now, which is 16c, which we're going to look at some further exponential functions. So ones that don't necessarily start at 1. So with that being said, that's the end of this video, and I'll talk to you guys in the next one.